Thank you, everyone. Right, and thank you for the introduction. So, what I sort of moved away very slightly from the title that I gave, um, and partly when I went back and looked at the report, one of the things that leapt out at me, of course, was the priority 5 that was mentioned, which was the formulation priority, and I sort of started thinking, okay, so what are the if someone turns up tomorrow at CPI's door and asks, right, how can you help me with the formulation or reformulation of a product because we're trying to move away from using PLFs. What can we do? What do we have that can help people? So that's really what I want to sort of structure the talk around. So we know that so as you say, formulation is one of the priorities. What I'll also do in the course of the talk is I will actually end by just discussing whether the little cartoon image that was featured in the was actually I have a suggestion for an alternative. So speaking before the break, very kindly introduced the catapult, so I don't really have to. We sit in this sort of space, so which in between sort of research and invention and commercialization. Two words I want to pick out of our vision here are sustainable and innovations. Okay, so that's what we're about. For those of you who don't know us, we serve the process industries, which is a very broad description, so of which sort of chemical using industries are a part. And we have a number of expertise and capabilities. Some of you might be interested in the fact that we also have biotechnology expertise. If you are, my boss's boss is sitting on the second row in a check shirt there, Chris Wadrup. He's the best person to go to ask about that if you want to catch him afterwards. But I'm really going to be focusing on the formulation and materials part, which is also supported by our digital capabilities. And don't attempt to read this slide. Really just wanted to focus on the sort of the formulation sort of areas that we serve. And if you scan your eye along this row, you'll see, I think you'll see things that are relevant to all of your industries and all of your areas. And many of them are called out as areas where PLFs are an issue. Okay, so I said we're addressing the formulation priority. Okay, so again, part of the work's already been done for me today in terms of describing what the problem is. This actually is the shampoo that I used this morning to wash my hair. I've turned up here with clean hair, you'll be pleased to know, and there's about 20 ingredients there. So one of the problems with when you're looking at formulating or reformulating, you've got combinatorial complexity to deal with. You've got multiple ingredients, potentially at multiple levels, and some of those things don't like each other. A former director of formulation used to talk about synergistic effects in formulation, which is what you want to achieve, but also sometimes you have antagonistic effects. Things don't want to be together. You have instability issues. And also, you can have competing requirements, competing critical quality attributes and critical process parameters. Very simple example, when it's familiar to everybody, if you are painting, when you apply the paint to the wall, you want that paint to have a low viscosity. You don't want to be forcing the paint onto the wall. Once it's on the wall, you want the paint to have a high viscosity, so that it doesn't sag down under the action of gravity. So you've got two different viscosity regimes under different, two different viscosities under different shear regimes. So those are two sort of competing things. Now, the paint industry has solved this years ago, so much that that piece of fantastic thing, we don't even notice it anymore. But that's sort of one example of these sort of competing issues. And then also been mentioned, I think today, scale up can be an issue as well. So you get formulation on your bench, works wonderfully, try and scale it up, it all falls apart and it's horrible and you can't manufacture it. So scale up is an issue as well. So now I wouldn't have mentioned those three problems if I didn't think that we had CPI could help people offer solutions to these things. So in terms of attacking the combinatorial complexity and these sort of competing issues, we have a suite of laboratory automation that's available, and all the things, as I say, are sort of are open access essentially. That's backed up and supported by some techniques around data analytics and machine learning that I'll talk about, and then also hopefully I'll have time to talk about tools for process scale-up, because I think just gone blank on the gentleman's name, Peter, I think Peter Clark from IUK. He mentioned about access to scale-up being an issue. Hi, give us a ring. Okay, we have scale-up facilities. We can take you from 1 mil, sub 1 mil, up to, I forget, at least 1,000 litres, probably bigger. Okay, 1,000 litres certainly at Sedgefield, and with some of our sister sites around CPI, probably even greater scales. So we have scale-up facilities. Okay, so just a quick breeze, an introduction to 3 of our automation platforms. The first one was built to our design by a company called Chemspeed. You've actually seen one of these, similar one of these already, actually, if the design looks familiar, because the MIF have some of these systems as well. They're great systems. They can handle a very wide range of materials, viscous liquids, mobile liquids, pastes, semi-solids, powders. Essentially, if it's feasible to dispense it, other than sticking a spoon into a jar, then these systems can handle it. It's a very nice variety of mixing systems. And the nice thing, and the thing that we got Chemspeed and worked with Chemspeed to do to get the customization on this, is that we've got at-line viscosity and rheology measurement. The rheometer is actually just sitting off here. That's the little arm that serves the rheometer. So you can actually look at the rheology profile of a material as it's made or as it ages. So because we thought that rheology is such an important property in formulation manufacture, we wanted to make the effort to do that. And we have some other say pH monitoring, also particle size analysis. It's sort of bigger brother in our automation lab. Was again custom built for us by Northeast company, actually, or Yorkshire company, Labman. Some ways similar sort of capability. It's probably get a sense that it's bigger. That means that you can handle more samples simultaneously in a run, which can be useful to have bigger runs. One of the key things that this gives us is this, you probably see this is a sort of a glove box type arrangement at the end here. So we've got the capability to handle sort of air sensitive materials, or materials that you wouldn't want to expose to air, but also nanomaterials, so substances, high active ratio nanoparticles, things like that. So so that's really sort of useful for certain applications, probably not directly of relevance here, but things like battery materials, things like that. And then we've also incorporated some other at-line measurements that we couldn't fit into the other system, particularly sort of surface tension, again, really important characteristic. Okay, so those are 2 sort of, for those of you that know lab automation, those are 2 classic lab automation systems, something big and complex inside an interlock cabinet. Something that we've been looking at recently, and actually we worked with the University of Liverpool on sort of up and during COVID times, and now we've invested in ourselves, are these mobile robots. So this is, instead of essentially piling all the complexity into a box, you think it really addresses the problem of, well, can you get a robot to operate in something that looks more like a lab environment? So you'll see sort of behind this, you'll see there are sort of conventional pieces of laboratory equipment that the robot can interact with. And the robot, the concept is sort of in simplicity itself, really. It's a multi-axis arm, essentially on a mobile platform. And a lot of the cleverness is in the mobile platform that has lots of sensors so that it detects if there's a person or other object nearby and will stop. And also it has, you teach it a map of the environment that it's going to operate in. We've got one of these now operating in the lab, and I think this is a major revolution in automation. Actually, I think will bring automation into a lot more environments. Okay, not a terribly exciting or novel technique, but something I want to mention now because it provides context for something else I'm going to talk about in a moment. Design of experiment, it's a natural thing that goes with automation. So the ability to essentially think about and create an optimized set of experiments that covers a parameter space. Really useful way, as I say, a natural way for automation to operate. It's generally regarded that it does reduce experimental time when you're covering a sort of a parameter space rather than trying to just vary one factor at a time. Does have its limitations though, and when you're faced with complex formulation challenges, so I mentioned like my shampoo, which has about 20 ingredients, I think, depending on how you count them, but it has about 20 ingredients in it. When you've got that, and you can imagine trying to reformulate that at maybe multiple levels, you start to do the combinatorial, and it starts to become a lot of experiments. If you're doing that with difficult materials that just take a long time, so each individual experiment does actually take a long time, then it actually becomes slightly unfeasible to do, and design of experiment really just starts to struggle. And even with automated facilities, the reformulation problem gets difficult. So just going to give a couple of examples of things that are trying to address that. So we've been working with a great company down in Cambridge, Intelligence, who've developed, I don't mind giving them a plug, they've developed software, Alchemite, where they've incorporated a machine learning model based on neural networks into their software. And essentially what this can do is this helps you, if you give it a basis set of a few experiments, it will then predict what's the next best set of experiments to do. So this means that you can design your experimental trials on a sort of smaller set of materials. And that's really important. I was talking to someone yesterday, and I actually asked them, I said, oh, well, hang on, why didn't you do that project on one of the robots? And they said, well, there was only a litre of this novel material that existed in the world. Again, it's not a PLF, but it was a sustainability-driven replacement material. But there's only a litre of this stuff, and we'd been given 500 mils of that by the company that we were doing the project for. Okay, so you couldn't really use then, so they had to then make the best estimate. So sometimes you've not got a lot of material to play with, or the material's very expensive. So you want to try and do fewer experimental runs and do fewer experiments. And it's showing both theoretical and with practical experience that doing this sort of optimized DOE, they call it, using this machine learning approach based on neural networks, you can actually step through the parameter space in a much more efficient way than you could do if you were trying to do a conventional DOE. If anyone wants to know a little bit more about how that works, I'm happy to talk to them later. I don't know all the details, some of it's proprietary, some of the material is published. I can point people to that. The other way you can do this is, instead of throwing lots of candidate materials at a formulation problem, you can say, well, okay, hang on, let's use what knowledge we have to try to cut down the number of candidates. And so one of the techniques we've used, and in fact it's a technique we've seen already, actually, I think it was Steve who showed a dimensionality reduction plot, the TSNE plot. And there's various different ways that you can do this. The simplest way, I thought, is principal component analysis, where essentially we asked the scientists, we had a problem where we wanted to find a new solvent mixture for an ink, or we were asked to find a new solvent mixture for an ink. And so the scientists sat down and thought about, okay, so 10 properties that they thought were relevant. And of course, if we thought in 10-dimensional space, if we were able to do that, then you could plot, the positions of each of the solvents in 10-dimensional space and go, oh, okay, well, let's try that one, but those two are close together, so we'll just choose one of those, and we'll try that one over there, and that one over there. Yeah, but of course, you can't think in 10-dimensional space. And I think even with the digital catapult visualization capabilities that they've got up in the Northeast, I still don't think we'd be able to think in 10-dimensional space. So what you can do is use techniques. I think PCA is now called a machine learning technique. It used to be just called a multivariate statistical technique to reduce the complexity down to a couple of dimensions. And you go, oh, okay. The ones in red are the ones that were chosen. I think they chose a couple here just to be close together as a test, but then just chose, 4 or 5 others. And that then they could then do a sort of a sensible and reasonable number of iterations, just 34 experiments, to find the optimal solvent system. You can do the same thing. Doesn't have to be just with solvents. This is actually with lipids, choosing lipids for lipid nanoparticles. So lipid nanoparticles, really important, used as a way of transporting RNA. One of the COVID vaccines was based on, at least one of them was based on lipid nanoparticles. But a bit of a real difficult formulation problem because they're made up of 4 different types of lipids. And if you look in the publicly available lipid catalogues, there are thousands, tens of thousands of lipids to choose from. So how do you choose which lipids thing? So again, we've used these dimensionality reduction techniques to find lipids that are similar to each other, and then if people just want to explore that space, they can do, or if they want to find things that are looking a bit different, they can do that. Okay, so I've sort of talked about the lab automation and the data analytics machine learning techniques, and I've managed to talk sufficiently quickly that I've got 4 minutes left according to my timer, so that's good. So I've got a bit of time just to talk to you about tools for process scale up. So as I said earlier, it was mentioned that, you know, is there access, public access, you might say, to scale up facilities? And as I say, I'd say yes, the answer is yes. It certainly is at CPI. I'm actually going to start back with the robots, funnily enough. So back in one end of the ChemSpeed robot that I talked about right at the start, there are these things that are rather prosaically called formulation vessels. I really wish they'd thought of a better name, but they do, as they say, you know, they do what they say on their tin. They're essentially miniature stirred tanks, stirring from the bottom in this case, about 100 mils volume, and you can use those, as I say, as a sort of miniature. You can sort of formulate in those, and that's great. But then, well, how do you go from 100 mils to 1 to 10 to 100 to 1,000 liters? And so one of the ways that we've tackled this is by using CFD modeling. So we have a CFD modeling capability at CPI. So using CFD modeling to understand the mixing in these and understand the mixing in our larger tank systems. And one of the key bits of learning from this is by understanding the mixing at larger scales, we can use this to constrain the mixing at smaller scales. Because it's dead easy when you're on a bench just to turn the wick up on your stirrer and have a little stirrer bar going faster. But that might be creating an environment that you can't replicate in your 1,000-litre tank. So yes, that's sort of one of the many sort of learnings from this. One of the other areas that we've been looking at, and again we've developed a number of we've run a number of projects on, is this area of soft sensors. Now, I'm not sure as I can say that soft sensors were invented in the Northeast, but they were certainly nurtured in the Northeast by Julian Morris and his group at the University of Newcastle. So what is a soft sensor? Okay, well, before I go into that, you know, just to say, ideally, when you're running a process, and when you either whether you're scaling up or you're running a manufacturing process, you'd like to control on the critical quality attributes. So you'd like to sort of say, I want to run this process to get my emulsion to a particle size of blah, or, you know, I want to aim for this viscosity level here or whatever. But they're often only accessible by offline measurements or by implementing expensive PAT. So PAT, people not familiar with the acronym, process analytic technology, it's basically taking research grade instruments and strapping them onto a manufacturing line. But it's not always feasible to do that. Either technically or commercially. I mean, it can be really expensive. Sometimes some of our pharma colleagues particularly tell me also there's regulatory issues as well sometimes associated with that. So, okay, what's the alternative? Well, the soft sensor approach, if you combine inputs from the sensors or the data you have already, then you can sometimes use this to infer something that you're really interested in. So, as an example, this data here is actually inferring viscosity from the pressure drop along. I think the team had put a sort of a few kinks in a pipe and then measured the pressure drop along there, and then the pressure drop relates directly to the viscosity of the material. So this sort of doing this sort of building these sort of soft sensors, it gives you access to much more information about your process than you might have already. And we've shown things like, typically, we managed to sort of example, this was, we used a shower gel to actually build the model, and then applied it to shampoo. So it's transferable across between systems. The final thing I want to talk about, and actually I think, Andrew, you mentioned right at the start of the day, if people can remember back that far, about the need for maximizing manufacturing efficiency. And one of the techniques that's been developed, and again, we worked with this company, Predictive Engineering, certainly to help introduce this technique into the sort of chemical and using and formulating industry, is model predictive control. And model predictive control takes that sort of soft sensor idea I was just talking about, but just takes it a sort of step further, where if you essentially build a machine learning model that connects the things that you can measure or control in your system, the things you can control in your system, which are often things like stirrer speed, circulation pump speed, things like that, and the things that you want to measure, so a particle size measure, viscosity. Okay. And you have to do, there's no magic here, so you have to do a few tests or experiments to actually build the model first off. But then once you have the model, you can sort of invert the thing, and you can use it to then control the system that you are operating. And it has been shown, and it's used now extensively in a number of industries, that this can operate plants in a much more efficient way, because you've got a system where you're automatically controlling for the things that you want to to make. So you've got much lower risk of, for example, wasted material, wasted run. Yeah. So that's again another one of the final one of the techniques that I wanted to talk about. Okay. Right. I am slightly over time, so I'll stop talking in a moment. So just a sort of a quick conclusion. Yeah, CPI, I hope I've just showed you and proved to you, CPI has got a suite of tools based around lab automation, data analytics, machine learning, process monitoring, scale up. And I say, key thing, all of these tools are available today, there's a big list of names down there, acknowledgements, obviously, I'm talking about lots of other people's work. But the final thing I wanted to say really is just to sort of refer back to this diagram is, this diagram showed people in a lab with test tubes and flasks and things. And really, I think we need to change that image, because really the solution is much more around these sort of tools. Okay, thank you very much for your attention.
Well, thank you very much. That was really informative, really, on the capabilities that we have at our doorsteps in our national assets in the capitals. Just one very short question to you is, if somebody was to want to have access to your facility, do they go via you, or is there like a system how they can actually access that?
Well, yeah, by all means, just phone me. There's my phone number. The more useful answer to your question, though, is yes. We offer sort of fee to service, so direct contract, essentially direct commercial contract. We also do a lot of CR&D work. So if you want to work with us to develop a proposal, then that's good as well. If you're sitting there thinking, I'd really like to work with these people, I've just got no idea how I'm going to fund that, call us anyway, because we've got very clever people who really understand the funding landscape, work with people like Peter Clark and others at IUK, their counterparts over in the European Union with Horizon programs. So just give us a call.
Thank you very much, Mark.